perturbations, you had the states switched.
Yes.
That cut. You meant the composition of states.
Yes.
Does that mean the basis states that go to form the states that make up those curves switch? Is that what you're saying?
Yeah. I mean, you could. So let's. When you have a weakly avoided crossing, you get this kind of a behavior, and so up in here, this would be an electronic state, has an electronic configuration, which is the same as or similar to the electronic configuration down here.
Okay.
And so what happens is you have a mixture, you have, say, configuration number 1, configuration number 2. And near here, all of a sudden, you go from almost pure configuration 2 to almost pure configuration 1. And right here you have a 50-50 mixture. And so the electronic character is hardly changing at all until right here, where it changes very fast. And that leads to gross violations of the assumption that the wave function is independent or approximately independent of internuclear distance. And as a result, there are large couplings that are outside the zero order model, and you have to put them in order to get the truth. And so when you have really, really weak configuration interactions, really, really weak electrostatic perturbation, then you get this cusp. If it's really strong, you get a kind of behavior sort of like this, and you hardly know that there was an avoided crossing, because the two halves of the avoided crossing are so far apart, and because there is so little anomalous curvature, you don't really know that this is different from a simple picture of what you expect to go on. Okay, and that also tells you that probably the adiabatic curves are the good way to think about the problem. And another way of knowing that is, if you have something like this, half the distance of closest approach is the electrostatic matrix element, which is enormous. And you don't want to have something enormous off diagonal in your model. It'll still work, but the model won't look like, or what's on the diagonal of the model won't look like what you've observed. So this is, I mean, it's really important to distinguish between the model, which puts, and in fact, this is what I left off. I didn't have a chance to finish properly at the end of last lecture. And so we have a model where the Hamiltonian might consist of 3 terms. We'll call them A, B, and C, but one might be electrostatic, one might be spin orbit, one might be rotation. And you have a choice of what you put into the zero order picture. You could say, for one case, you have A plus B in the zero order picture, and in another case, you might have A plus C. It implies that B and C are incompatible. And so in your zero order picture, you're out of luck. You don't have electronodes. Okay, so we'll make a copy and we'll. But what I'm talking about right now isn't in anybody's lecture notes. Why don't I, before we go on, why don't I circulate this list? If you want a PDF copy of the typed lecture notes after they're proofread and so on, put your name and email address here, and Peter will send them out. So the first lecture notes are nearly ready, and the second ones will probably be ready tomorrow. Okay, so B and C are operators which are incompatible. In other words, you can't have states which are eigenstates or of both B and C. Or you can't find a representation in which B and C are both diagonal. You can diagonalize A and B simultaneously and A and C simultaneously, but not B and C. These are two mutually incompatible terms in your picture. And you always make a choice. There are always going to be mutually incompatible terms in your model for what's going on. And you have to choose which one is the one that is better to put into the zero order picture. So you'll capture most of the important structure that you're going to see in the experiment. And then you put the other one in as a perturbation. And you then use the eigenstates of the part of the problem you've chosen to make H0 to evaluate the effects of the missing part. And this is, basically that's all spectroscopy is. In fact, I would imagine that's pretty much all any representation of a complex situation is. That you say, this is the part that is that captures most of the problem, and that I can describe it in a convenient way, and then I put in the other part as some kind of a perturbation term, which I also treat accurately and honestly and completely, but only as a modification of what is the fundamental simplicity of this particular situation. And let me be a little more specific. In the Hamiltonian for a diatomic molecule, we have a contribution from the spin orbit operator, the spin orbit constant times LZ SZ. This gives rise to the spin orbit splitting of a multiplet state. And we also have a term from the rotational Hamiltonian, the rotational constant times J plus S minus plus J minus S plus, where this is called the spin uncoupling term. This is off diagonal between states of different values of the projection quantum number Jz and the projection quantum number for Sz. This is called omega, and this is called sigma. So we could choose a basis set where this is diagonal, and as a result, this goes into H0. And this is not diagonal, and this term we call the perturbation term. And it leads to small modifications of a characteristic pattern, which is easy to recognize. And that's called Hund's case A. Or we can put this in, and this forces us to a situation where the good quantum number is n, which is J minus S. And then the rotational levels go as B times Nn plus 1, and there's nothing from the rotational Hamiltonian that's off diagonal. But this is off diagonal. And that's called Hund's case B. Now, let me also take something from the last page of the notes from last time that we didn't get to. So, let's say we have two Hamiltonians. Hamiltonian number 1, which has the form delta over 2, 0, 0, minus delta over 2. In other words, a splitting of the states on the diagonal of delta. So there's some term in the Hamiltonian that lifts a degeneracy, that creates a pattern. And there's going to be another term in the Hamiltonian that tries to destroy that pattern. Now, for a 2x2, it's easy to do all the algebra. But generally, the problems we deal with are a little bit bigger than 2x2, but not much bigger. But pattern is much harder to see, and the amount of crank turning to do the algebra is much more severe. So the other Hamiltonian is 0, 0, B, B. This is an off-diagonal Hamiltonian with no difference in energy on the diagonal. So our full Hamiltonian is the sum of these two. Now, we can use a basis set where this Hamiltonian stays diagonal. But then there's going to be this thing here, and we either do corrections by second order perturbation theory, which would be correct the energies by v squared over delta, provided v over delta absolute value is less than 1. That's the convergence criterion for perturbation theory. When v over delta is not less than 1, then we actually have to diagonalize this matrix. Now this is an easy matrix to diagonalize because the diagonal elements have the same energy. I can write down the transformation to diagonalize that without thinking. So what I'm going to do is go to the basis set, or go to the eigenvectors of this. Okay, and those are 1 over square root of 2 times 1 plus or minus 2. Where these are the eigenvectors of this. Okay, it's for the people who only had 561, or who haven't had 561, this is a reach, but I want you to get this. For my students, this is not a reach. But this is really a crucial point. Okay, so this will diagonalize this Hamiltonian. And how do we know that? Well, let's calculate the matrix elements. So okay, so this is the symbol. Let's take the diagonal, the plus with the plus, or the minus with the minus. So these are actually two elements at once. And this is plus with the minus, or minus with the plus. And so we're going to have the wave function twice, so we'll get 1 over square root of 2 squared, so we'll get a half. And then we'll have h211 plus h222 plus or minus h212 plus or minus h221. Okay, so in H2, these two things are 0. And these two things are both V. And so we get plus or minus V. And when we go through, so we're just putting this in and calculating the matrix elements of these things. Now, I can do this sort of almost in my head, but this is going to require a little bit of study from people who haven't done it before. Okay, but I want to write it out so that you can convince yourself that you can derive that. It would have been easier if I just wrote an extra line on the blackboard. Okay, for the second one, we have a half times H11 for Hamiltonian number 2 minus H22 for Hamiltonian number 2. Minus or plus H12 plus or minus 21. And these are 0, but this is V and this is V, and so whichever choice of sign we choose, we get 0. And so H2 transformed, you can give it that little symbol, looks like this, V0, 0 minus V. We go through the same thing for H1. And I'm just going to write that down. For H1, when we transform H1, we get 0, delta over 2, delta over 2, 0. Doesn't that look interesting? This looks almost like the old H2. We have the same number off diagonal, nothing on diagonal. And this looks like the old H1. We have the same number, but with opposite sign on the diagonal. So if we choose to choose one basis set, we have one term on the diagonal creating a difference in energy between the states, and the other term off diagonal, trying to spoil that picture. If we choose the opposite basis, the roles of the two terms, the good term and the bad term, switch. And good becomes bad and bad becomes good. And this is everywhere what is happening. And sometimes, in order to understand the mechanism of what's going on, it's necessary to make one of these transformations. And the reason for some off-diagonal interaction between states that leads to some dynamics or some complexity in the spectrum is much clearer in one representation as opposed to the other. And one example of that, which we might get to today and might not get to at all, is rotational autoionization. I'll get to that. I'll talk about perturbations now. Okay, so this is what was left from the last lecture, and it's probably the most important point from the last lecture. We have always mutually incompatible terms of the Hamiltonian, and we choose one to go into H0 and the rest to put off diagonal and treat as perturbations. Every choice, when you do the problem completely, including all the off diagonal elements, gives an equally good representation of reality. But the different approaches, when you ignore the off diagonal elements, give very different correspondence to reality. An appropriate representation gives a recognizable description of reality, where there are small deviations. Okay. The crucial actor in our treatment of molecules was the Born-Oppenheimer approximation. So I keep dividing up the Hamiltonian slightly differently. We have the electronic plus vibrational Hamiltonian. And then we have spin orbit and the rotation Hamiltonian. The reason I put these together is that when we do the Born-Oppenheimer approximation, we generate the potential curves. And once we have the potential curves, we solve the vibrational problem. And whether we make a diabatic or adiabatic choice, we get different potential curves, so the vibrational problem is different. But it's the same crank you turn. You have potential energy curve, and you have the nuclear kinetic energy. You solve the nuclear Schrodinger equation, you get eigenfunctions and eigenvalues. Okay, for diatomic molecules, the most convenient, from the point of view of writing down matrix elements and representing the problem, the most convenient basis set is generally the Hund's case A basis set. And so case A basis functions look like this. We have the electronic, a symbol that says which electronic state, let's call it with an I. And then we have L, which is never really good, but we often include it as a label. Lambda, S, and sigma, and then omega, K, M. So these are the quantum numbers, and these are our basis functions. And in order to make any progress with diatomic molecules, we need to know how to evaluate matrix elements of all operators in the Hamiltonian in this basis set. So, for angular momentum matrix elements, you want to look at pages 72 to 81 from my book, which I handed out until I ran out of copies. Some of you have it. It's in that handout. There's 3 pages that are with nice pictures, which I'll get to, and then there is the machinery. Okay, so let us say that A is an angular momentum. It's some operator, some angular momentum, and the nice thing about angular momenta is that once you know what the matrix elements for one angular momentum are, you know them all. And so we have the angular momentum squared operating on a basis function which is expressed with 2 quantum numbers. The quantum number associated with the total angular momentum and with a projection of that angular momentum. Projection on what we call the symmetry axis or the z-axis. Okay, we're free to choose, but in diatomic molecules you would be kind of stupid to choose anything but the internuclear axis as z, because that's an axis of cylindrical symmetry. But it turns out that for Rydberg states, sometimes the quantization axis is not the internuclear axis, but it's the axis about which the molecule rotates. And that leads to some strangeness. But, so you have a magnitude and a projection. And so you get A plus 1, A alpha. We have the space fixed, the laboratory, the body fixed z-axis projection. And that's alpha, A alpha. Then we have the raising and lowering operators, which are A x plus or minus I A y. And A plus minus on A alpha gives A plus 1 minus alpha plus or minus 1 square root A alpha plus or minus 1. And that's all. That's all you need. This is a small amount to learn in order to be able to address practically any problem in diatomic molecule spectroscopy. And the reason case A is nice is you have 3 important angular momenta, and each of them have their projection specified. So that means it is completely transparent to write matrix elements of A squared, AZ, and A plus minus. There isn't anything else. So you don't have to use Clefts-Gordon coefficients or 3J coefficients if you're in case A. So even for situations where case A is inappropriate, many people prefer to use case A because it's easy for them to set up the machine that represents their spectrum. Now, there's no big deal using 3J coefficients to deal with angular momenta, coupling and uncoupling. And if you're going to be a professional, you want to be able to work in different basis sets and to transform between them using the vector coupling or 3J coefficients. And you can get a computer routine that will calculate any of those you could ever need. And so the only difficulty is that 3J coefficients are expressed, angular momentum transformation coefficients are expressed or are labeled with 6 quantum numbers. And so somehow you have to think about 6 quantum numbers. And after a while it becomes not so hard. But this is a more linear approach in some sense. Okay, so I've said enough about that. If you're going to start out doing diatomic molecules, I strongly recommend case A. Yes?
Can you remind us, I can't remember, is there any obvious way to look at a diatomic molecule and guess whether it's going to be case A or B?
Yeah, sure.
Is it has something to do with the size or the type of atom?
A
Or do you have to look at the J splitting?
Versus B J.
Okay, so all you have to know is the spin orbit.
That's right.
The rotational constant and upon.
That's right. And so A is small for the beginning of the periodic table, and it gets larger and larger. And B is large for hydrogen and large for molecules that have one hydrogen, and sort of intermediate for molecules that have 2 second row atoms like CO. And for heavier atoms, B is very small. And so as you go down the periodic table, the heavier molecules, you tend to go towards case A. But if lambda is 0, in other words, sigma states, you're always in case B. But it's not a big deal. Okay, now I said it was easy, but there's one little patch. If you want to do this without thinking, you have to say, oh, Bob told me that if we have an angular momentum that controls the rotation of the body fixed coordinate system relative to the laboratory coordinate system, then I have to make a small patch. And it turns out that J, N, and R. J is the total angular momentum. N is J minus S, the total angular momentum exclusive of spin. And R is the nuclear rotation. Then J plus lowers omega instead of raising it. N plus lowers. R plus. Well, R plus can't really do anything because there is no projection of R on the internuclear axis, because R is, we have a diatomic molecule, and R by definition is perpendicular. So, but these angular momenta have some special property, and you can understand that when you look carefully at the transformation that takes you from body to laboratory, direction cosines. And when you work, when you develop more facility with the true classical mechanics and quantum mechanics of the system. Okay, but right now I just say this is a patch, and basically you are now empowered to do all calculations on diatomic molecules, at least as far as the angular momenta are concerned. Okay, now if you want to deal with the nuclear motion, That's another topic which I will address. Okay, so now I make a little table of all the angular momenta you're likely to encounter. Well, a lot of them anyway. So we have the operator, the quantum number, and the selection. So J squared, JZ, J plus minus. I'm not going to be able to do this all on one board, but you'll get the idea. So operators are generally represented as a bold face. Oops, plus minus. J has two projection quantum numbers, one in the laboratory and one in the body. And so I've chosen to use the superscript for body and subscript for laboratory. You encounter that less often. And so I'm not even going to talk about it. So we have the quantum number is J, and for J squared you get JJ plus 1. And the quantum numbers are generally written as italic. The selection rule for J squared is delta J equals 0, delta omega equals 0. The quantum number for JZ is omega, delta J equals 0, delta omega equals 0. There is no quantum number for this operator because it's an off-diagonal operator. And the selection rule is delta J equals 0, delta omega equals minus or plus 1. Similarly for S squared, S, Z, and S plus minus. SS plus 1, sigma, delta S equals 0, delta sigma equals 0, delta sigma S equals 0, delta sigma equals 0, delta S equals 0, delta sigma equals plus or minus 1. And we can go on for a long time. Now we come to L, or L squared. Because a molecule isn't spherical, L is usually not defined. But we can still define LZ, and we can still use L plus minus. So we don't have a quantum number here, although we'd like to write LL plus 1. And we don't have a quantum number for a selection rule for L because we don't know what L is, but we still have delta lambda equals 0. And here we still have delta lambda equals 0. And here we have delta lambda equals plus or minus 1. There are other quantum numbers like, or operators like N, which is J minus S. And it turns out that NZ has the quantum number lambda because NZ is identical to LZ as far as the part that can have a projection, because NZ JZ is LZ plus SZ plus RZ. RZ, the projection of the nuclear rotation on the internuclear axis, has to be 0. And so JZ minus SZ is LZ. So LZ is NZ. Okay. Now we get to more esoteric situations, but I want to talk about them. Suppose you have a molecule which has sort of a closed shell or nearly closed shell core and an electron far away from it. And so this is an ion, and this is called a Rydberg state. When the electron is far away from the ion, it thinks it's on an atom, and we get L back. But we get not big L, but little l, the L for this Rydberg electron. And so we start having more quantum numbers. We have the quantum numbers associated with all of the angular momentum of the ion, and you have the quantum numbers associated with the Rydberg electron. So instead of having just some L, S, and J as our quantum numbers, we start having 6 quantum numbers. We have L plus, S plus, and J plus, and little l, little s, and little j, or something like that. So we still can couple them together. We can still use case A methods. And so we can have J plus. Now this is not the raising or lowering operator. This is J for the ion. We use plus, and you can tell the difference because when you have a bold operator, a bold symbol, it's an operator. And when you have an italic symbol, it's a quantum number. And so, and when there's a problem, when you have an operator and you want raising and lowering operators of it, then you put it in parentheses. Okay, and so the quantum numbers associated with the projection. Okay, so suppose we have the J plus Z. That would be called omega plus the quantum number. Okay, this is more detail than you need. Okay, so we just put a plus on the quantum numbers for the ion, and since this is a 1 electron quantity, we use lowercase letters, little j, little l, little s, little omega, lowercase lambda, lowercase sigma for the quantum numbers of the electron. So there isn't any ambiguity. There's lots of angular momentum, and there's lots of coupling cases. Remember when we talked about the coupling cases last time, I said we had 3 terms: electronic, spin orbit, and rotation. And we can arrange them in 6 orders of relative size. And that leads to the 5 known Hund's coupling cases and 1 other. But now if we have more quantum numbers, you can imagine how many coupling cases there are. But it's no big deal, because the same techniques you use to evaluate the matrix elements and rearrange terms of the Hamiltonian, there's nothing different. Okay, so you are empowered to deal with angular momentum in diatomic molecules, even if we have 6 rather than 3 important angular momentum. So what's left? Well, there's the vibrational wave functions. And let's talk about them. And I'm going to present a very, very important approximation that enables us to simplify our work dealing with vibrational matrix elements. Okay, so the vibrational wave function, we have, that should be a chi. We have a vibrational wave function for the ith electronic state, and then it's got a vibrational quantum number. It's a function of R. In Dirac notation, that object is the same thing as this. Okay. We tend to like to think of vibrational wave functions as functions, and angular momentum wave functions as vectors. Because we don't, I mean, this is a simple one-dimensional function, and we're going to be calculating integrals over it. There aren't nice angular momentum-like algebra for vibrational wave functions. Whereas angular momentum wave functions are treated by an algebra where basically all the matrix elements are directly evaluated, and you never look at the differential operators that correspond to the angular momentum, nor the forms of the wave functions. So it is tempting to look at these sorts of things rather than this kind of a symbol for vibration. Now, we have a wave function, which is a product of an electronic, vibrational, and a rotational part. So in order to calculate matrix elements, we're always going to be evaluating a product of three factors: a rotational matrix element, a vibrational matrix element, and an electronic matrix element. So the electronic part we deal with first, because we get rid of it almost immediately. So we have some electronic operator, and we have two different electronic states. And according to the Born-Oppenheimer approximation, these functions are parametric functions of internuclear distance. So that means that we're going to have this matrix element is going to be a function, an implicit function of R, internuclear distance. So the Born-Oppenheimer says, well, we do the electronic integral, it will be a number, but this number will probably weakly depend on R. Now, if this operator has an explicit dependence on R, that'll also appear here. Now, one operator that has an explicit dependence on R is the rotational constant, h bar squared over 2 mu r squared. Now, that's not an electronic operator, but so we're often going to have things that either implicitly or explicitly depend on internuclear distance. This is a problem because when we have an electronic property that depends on R, and we want to evaluate matrix elements, now I am writing the vibrational wave functions as Bras and Kent's here. So this is a vibrational matrix element. Once we've done the electronic integral, now we have to do the vibrational integral. If this is a function of R, we have big problems. We'd like to ignore the dependence on R. So, how bad is this? How bad a problem is this? Well, one can always expand this as a power series in R, and then evaluate all the necessary integrals. So that would mean we'd have things like just the vibrational overlap. We'd have VI R Vj. We'd have VI R squared Vj. We'd have to calculate lots and lots of vibrational matrix elements. And this would be inconvenient, and it would also be costly in terms of our understanding of the problem. And so we'd like to make that go away. So it turns out that we can always, or almost always, replace this kind of an integral with VI, Vj, a simple vibrational overlap, times Oj of R, VI, Vj, R. That's called the R centroid. The R centroid is defined as this quantity. The matrix element of R divided by the overlap integral. That's perfectly reasonable. It is the way you would define the average value of R. So the R centroid, this is the R centroid. The R centroid approximation says replace this integral of the function of R by the overlap integral, the only vibrational integral you're going to have to calculate, or not the only one, times the R centroid, this O of the R centroid instead of O of R. That's an approximation. It's a very good approximation. And it's based on the assumption that R, VI, Vj is equal to R n bar VI, Vj over R n minus 1 VI, Vj. This is the R centroid approximation. The R centroid is given by any value of any power of n, this ratio n minus 1. Now, why should that be true? It's astonishingly true. How can we expect vibrational integrals involving different powers of R to have this property? This gives us a hint of something that's going to be really important. The integrals accumulate always in a very narrow range of R. And that's called the stationary phase approximation. And we'll get to that, but that leads to really important simplifications, because often one can know explicitly what region, narrow region of internuclear distance the integral will accumulate in. For example, if we have a problem like this where we have two potential curves and they cross, and we want to calculate the vibration overlap between these two levels at about the same energy, the integral, the vibrational overlap, and any integral involving any power of R will accumulate in a narrow region at the internuclear distance where the two curves cross. And so for all vibrational matrix elements, there is hiding in here this stationary phase situation. This just means that when the two wave functions have the same nuclear kinetic energy, they're oscillating at the same spatial frequency. They have the same momentum. And the momentum gives you the de Broglie wavelength. The de Broglie wavelength, lambda, is h over t. And so if they have the same kinetic energy, they have the same momentum, they have the same wavelength, that means that at this point, they're oscillating at the same frequency. And so the integrand, which is the product of two wave functions, that integrand oscillates very fast, except near this point, and that's why the R centroid approximation works. And we'll return to this when we talk about the semi-classical approach to everything. Okay, but the R centroid approximation is very convenient because in order to deal with these kinds of matrix elements, one has to calculate only two integrals, this one and the integral involving R. The R centroid is this over that, yes. So there's only, for every pair of Vi and Vj, instead of having to calculate matrix elements of all powers of R, one just calculates the overlap and the matrix element of R to the 1 power. And that leads to tremendous simplification of effort, and it also allows us to describe things in a way that's much simpler. The observables sample the R dependence of electronic quantities only in the vicinity of some special point, which you know, and so they're not terribly sensitive to curvature, to strange variations. And so one can ignore the R dependence of electronic quantities for most calculations. This is very helpful. And it would not be clear if you were simply doing numerical calculations, because you would always do the numerical calculation correctly. And you'd be doing, you know, you'd turn the crank and you'd get something, but you wouldn't know that everything interesting is happening in a particular place. And the nature of your wave function at that internuclear distance is what determines what happens in the experiment. And a different experiment might have curve crossings at a different R, and it might sample a wave function in a different place and give you something else. Okay.
Bob?
Yes.
So where would this would break down if you had, say, 2 peaks? If your wave function had 2 maxima, and would that be a case of where
No.
it breaks down?
No. It'll break down when you have something like this, where there's no spatial overlap between the 2 vibrational waveforms.
Because then R will be in the middle.
It will try to be somewhere here, and so it's in the tails of the wave functions, and so there's just
You're gonna get a
no.
weird value for the electron. That's going to be really high because it's really high on those curves, and the wave functions aren't even there.
That's right. So when you're dividing by 0, you don't expect to have very much of a purchase on whatever it is you're calculating. So when the overlap integral is really small for a good reason,
Right.
as opposed to because of an accidental cancellation, then the R-centroid approximation really fails.
I was just wondering if the wave functions happen to have 2 maxima, and those happen to be, if they had 2 maxima, basically essentially what you're calculating is the average value of R with with the R centroid, right? And so if you had 2 maxima of the wave function, the average value of R might turn out to be in between them.
But that's okay, because the wave function isn't 0 except at nodes.
Right.
And so what you're basically doing is you're measuring at this special point what is the classical probability, which is related to the classical velocity, or 1 over the classical velocity, which is related to the classical momentum. So you can still have small vibrational overlaps and still have the R-centroid approximation work, because it's basically telling you that it's at this place, and the two vibrational levels correspond to the particle moving really fast in that region, but it's still classical. You still get the results by using classical mechanics in a semi-quantum mechanical way. It's almost always true that you can use classical mechanics embedded in a quantum mechanical framework and get the answer. And when you do that, you get what you're told you're not supposed to be able to get from quantum mechanics, which is where does something happen? In quantum mechanics, it says this is the probability of something happening. But in classical mechanics, you're watching x and p as a function of time. And you can say something happened at this position and at this time, and the particle was going this fast. And so you know what the forces were, and you know, so everything starts to have interpretation when you can embed classical mechanics in quantum mechanics. So quantum mechanics says you're not supposed to know this stuff, but usually you can. And whenever you have an approximation like this, saying, you know, everything accumulates, I mean, the only way you can have the R-centroid approximation work is if things accumulate at a specific R.
I mean, I think this is what, I mean, Dave's question kind of recast is if you have two different potentials
Yes.
and they both have all their, you know, you're in a high vibrational state, you have all the probability at two sides of both.
Yes.
So if you're calculating an overall electronic integral between those two,
Yes.
you're going to say the R-centroid's in the middle and there's nothing there because all the action happens at the sides of both.
But classically, you know how much, you know what, I mean, there isn't nothing there, there's a little bit there. And you know exactly how to calculate that. Because in the middle region where things are going really fast, it's a lot of oscillations. And so there's not going to be...
But then you're saying that the electronic, whatever electronic integral you're calculating is determined by that point, when you think it would be determined by where all the vibrational amplitude is, the turning point.
But you would be wrong. It's determined where the stationary phase is. And it's determined by how much time the particle spends in the stationary phase region. What does that mean? Well, we know a velocity. And we ask, well, what is the stationary phase? How far can it go before the two wave functions get pi out of phase or accumulate a pi phase error? So the integrand, the integral will accumulate about the stationary phase point over a length which is determined by how far you can go before the two wave functions develop pi phase difference. And that's related to the difference in slopes of the potentials. And the value that accumulates is the classical envelope, which is 1 over the velocity. And so you can basically evaluate this integral not by numerical integration, but by classical mechanics. You need to know the period of oscillation, the velocity, and the stationary phase point, and how long is the stationary phase region. And all of those you can get simply by looking at the potential terms. And the fact that the wave functions have big lobes that don't overlap with each other, it means that the integral is going to be small, but the value of that integral you can calculate. And you can use very simple ideas to get these integrals to factor 2 accuracy, or you can use Airy functions to get the integrals to whatever accuracy you want, and to have all of the, you know, the dependence on energy and other stuff. Are you?
I still don't believe.
Well, what if you have two stationary phases?
If you have two,
If you have two stationary phase points, you're screwed.
Well, yeah, I'm not saying that you have
That's what
each wave function separately has a lobe,
two stationary phase points.
Well then,
and then you end up with an average in the middle. That's right. That's exactly that's.
if you have two stationary phase points, then semi-classical arguments will not help you, because each one is going to generate a large contribution to the integral,
Right.
and you don't know their relative phase.
And you end up. I mean, it seems like R average is in the middle, even
Well,
though
what
the
you will
overlap's
find
occurring both at the edges.
When there are two stationary phase points, if you calculate the R-centroid for several different successive vibrational, it'll jump all over the place.
Okay.
So there'll be warnings.
Okay. So that's your warning, is that you're.
Yes. So, and you can tell, I mean, you have two potential curves, and you subtract the two, and you look at the difference potential as a function of R. The stationary phase point is where the difference potential has zero derivative. And if there's 2 or 3 places where it has zero derivative, you're warned. And sometimes you can get away with it because there's only large amplitude at one of those. If there's large amplitude at several of them, or small amplitude at all of them, then you're going to have to worry about the relative phases, and that's where quantum mechanics does stuff that classical mechanics can't touch. I mean, there isn't interference in classical mechanics. You can still use classical mechanics to guide you to the one thing you have to get from the quantum mechanics. But often, there's no point. Once you've gone that far, you might as well use the quantum mechanics. Okay, we still have a few minutes. Okay, now we're on page 5 of my notes. So, the Born-Oppenheimer approximation tells us how to begin. And usually, life is a lot simpler than you have any reason to expect. That the spectra are really regular, that there are nice simple patterns, and that there is no hint that bad things are happening or could happen. And so there's two limits. One is the limit where Hij, the off-diagonal matrix element between two states that might be near each other, two zero-order Born-Oppenheimer states, or case A diabatic states, or whatever. So the matrix element over the energy difference is small. So this is the situation that leads to unexpected simplicity, undeserved simplicity. There are all sorts of off-diagonal matrix elements lurking, but none of them lead to observable effects or very important effects. When this is true, one can always correct the energies by second-order perturbation theory. So this is delta E. So the energies are corrected by this. This is small. It usually varies with state smoothly, and so you don't really see anything weird. But then there's the other limit, where this quantity is much, much larger than 1, and that's usually because of an accidental degeneracy. So there's nothing really in the Hamiltonian that says this is going to happen. It's just the levels, which you've normally been ignoring interactions between, accidentally fall near each other. And whenever that happens, you can't use ordinary second-order perturbation theory. You get local effects, and these are called perturbations. This regular thing is messed up. There is something that looks wrong, except there's nothing wrong about it. But it requires a special treatment because of this unusual energy denominator that brings these zero-order states close together and forces you to deal with the true evil of nature. Okay. There's many types of perturbations. One is we have a bound potential curve and another bound potential curve, and we have vibrational levels of this and vibrational levels of this, and they're near each other. And then if we look at the energy versus J times J plus 1, we get something like that. Remember, the energies versus J times J plus 1 will appear as straight lines with slope of B. And if you have different rotational constants, these curves will cross. So at this place where we have states of the same J that are degenerate, something bad is going to happen. And now suppose nature has said, well, I can excite to this level because we have a singlet ground state, this is a singlet state. But this is a triplet state. I can't excite to that. This is called a bright state. This is called a dark state. And so if I, well, now there's some pictures that I handed out. What is a perturbation? Here is a spectrum recorded on a photographic plate, which nobody ever does anymore, but it makes it so clear. You see this regular spacing of lines. That's an unperturbed spectrum. That's a textbook spectrum. There's no dynamics in it, nothing interesting. And that's what most people would like to see, because they're risk averse. And then this is just the next vibrational level higher in that same electronic state, and you can see there's something wrong. There's no regular spacing of lines. There are lines that have been shifted around, and there's extra lines. There's more lines in here. You see how many lines in this lower space? You see they're not just, there's many closely spaced things. And the reason for that is because you're not just seeing the bright state, but you're seeing the dark state. Because of this accidental degeneracy, there are level shifts and intensity borrowing. You open a window onto what you're not supposed to see. And some of us still get a thrill when we can look through a window we're not supposed to see through. All right, so we learn about other states. We learn about the coupling matrix element. We learn about dynamics. Okay, so I'd like to say more about perturbations, but there's another kind of perturbation. So we might have a bound state crossed by a repulsive state. So this leads to AB going to A plus B. This leads to a breaking of the bond. Predissociation. So we have a vibrational level here and a vibrational continuum here. And because there are coupling matrix elements between the bound state and the continuum, what happens is, if we look very carefully, the bound state gets broadened. It might get shifted, but since there's continuum above it and below it, it is not likely to get pushed one way or the other by more density of states above or below. So that level shifts are not important, but level broadening occurs. And again, on these pictures that I gave you, it shows the second picture is still another perturbation, but it's a small one. But this third picture shows something happening. Here is the absorption spectrum, and here is the emission spectrum. Same band. In the absorption, it doesn't care if the excited state can't live to emit a photon. But in the emission spectrum, if the dissociation rate becomes large compared to the spontaneous emission rate, you get no fluorescence. So this is a predissociation. And it's interesting, if you look closely, that there's a sudden drop in intensity and then it picks up again. That the dissociation rate is slowing down as you go away from the first J that is hit. And so you get a large variation in these mixings. So we can still describe predissociation by calculating the electronic matrix element times the rotational matrix element times the vibrational matrix element. And the complicated new thing is we have a bound vibrational state interacting with a continuum vibrational state. But there's still a stationary phase region And that's determining everything. And there is another kind of perturbation that leads to what we call autoionization. So we have a process AB going to AB plus an electron. This is harder to draw. Basically what happens is we have an electron bound to an ion, and the ion can have electronic excitation, spin orbit, vibrational excitation, rotational, and somehow the energy in the ion finds its a way to get into the electron, to transfer to the electron. And when it does that, the electron is too much kinetic energy to remain bound to the ion, and it falls off. And there are beautiful mechanisms that describe how this autoionization occurs. And each of the processes, electronic, spin orbit, vibrational, rotational autoionization, has a nice mechanism.